I want to introduce the current and voltage equations for a capacitor and for an inductor. Let's presume that I have a capacitor with a bottom terminal tied to ground, and it has a value of capacitance called C. And over here I have an inductor with this terminal also tied to ground, and it has a value of inductance L. If I want to write the equation for current in this capacitor I versus the voltage across the capacitor V, I come up with an equation. Current is equal to the capacitance C times dV dt. And I will explain what dV dt means in a moment. If I take the inductor, I want to do a similar thing. I want to find an equation for the voltage across the inductor versus a current I through the inductor. The equation is V equals the inductance times dI dt. Notice that the formulas between the capacitor and the inductor are similar. This quantity C is replaced with the quantity L for the inductor, and the voltage and current are reversed for the capacitor and for the inductor. Let's examine this dV dt term. What does that mean? Well, this D symbol is a term used in calculus that means a very small change in voltage. So when I say dV, I mean a very small change in voltage divided by dt, which means a very small change in time. So let's examine what that means. Let's presume that I have a graph of voltage versus time. This is my time axis, and this is my voltage axis. Let's presume that if I plot voltage versus time, that I get a voltage that increases, it levels off, then the voltage decreases. So when you see this dV dt, which is a concept from calculus, think slope. Think slope on a curve at any particular point. For example, if I take this point right here, and I want to find the dV dt, or the slope, it would be a line drawn like this. If I want to find the slope over here, it would be a line drawn along here. This would be the slope. If I want to find the slope right at the top, the slope would be flat. The slope would be essentially 0. So let's examine this region a little closer right here. Let's expand it so we can see things a little better. So the slope, I'll redraw it over here. Is something like this. So if I take a very small change in time, I'll call dt, and a very small change in voltage, I'll call dV. And if I divide dV divided by dt, you can see that I get this slope at this point here. And in this case, it's a little greater than 1 because the dV dimension is bigger than the dt dimension. If I have a steeper slope, say something a little steeper, and I take the equivalent dt, and notice that this dV is bigger, dV. So when I divide dV by dt, I get a bigger number, and I get a bigger slope here. So if I look at this curve, if the point over here has a positive slope, the point over here has a negative slope. Okay, why is that slope negative? Let's blow up this region. And the curve is looking something like this. So if I take a small change in time and a small change in voltage, my dV in this case is negative because my voltage is decreasing. My dt is positive, so if I have minus dV divided by dt, I have a negative number or a negative slope. So think of it this way. If you have a positive slope, for example, at this point, that corresponds to current flowing into the plus terminal of the capacitor. If I have a negative slope, for example, this point, the current is flowing the other way in the capacitor. It's flowing in this direction. If I have zero slope, corresponding to this point, I have zero current flowing in the capacitor. Now the inductor behaves in a similar way, except the voltage and the current terms are reversed. Instead of having capacitance, I have an inductance in this equation. So let's erase this. Now I want to show you a different equation for the capacitor and for the inductor. Let's draw a capacitor. I'll ground the bottom plate. And I'll call this capacitance C. Over here, let's draw an inductor. Again, the bottom terminal will be grounded. And I'll call this inductor L. Last time we calculated the current in the capacitor. Now let's come up with an equation for the voltage. The voltage V across the capacitor versus the current I in the capacitor. So the voltage V is equal to 1 divided by the capacitance C times the integral of I dt. The integral of I dt is a concept from calculus that I will explain in a second here. The equation for the current in the inductor, I, versus the voltage across the inductor, V, is I equals 1 divided by L, integral of V dt. Now notice the equation, again, between the capacitor and the inductor are of a very similar form. For the inductor, the L replaces the C, and current and voltage are swapped. So what does this term here mean? Integral of I dt. Let's investigate that. Let's draw a graph of current versus time. So this will be my time axis T and my current axis I. Let's presume that I have a current versus time, that current is more or less constant here, then it changes quickly, it reverses. Current goes negative and stays negative, say until this time here, it goes back to 0 and stays at 0. So this, when you see this integral of I dt, think area. Think area under a curve. For example, this I dt, this dt means a very tiny little sliver of time. You can think of that as a little sliver in time here. So I have dt, which is this little moment in time, very tiny bit of time. My current at this point is, I'll call it I. So the area of this little sliver is equal to A, I'll call it, a very small little slice of area, I'll call it dA, is equal to I times dt. Now this symbol here, it's sort of like a S that's been stretched in the vertical direction, means summation. It means that we're going to sum all these little slices over a certain period of time. That's all that means. So if I look at this area on the left side, and there's an area on the bottom. So if I compare this area here to the area below the curve over here, I see roughly they're about equal. So if I ask what is the voltage at this time right here, I could just look at this curve and I can kind of sum this area in my mind. I can say this area here is about equal to this area here. So they cancel out. The total area at this point in time sums to 0. So it tells me at this time the voltage is equal to 0. Now there's a little trick I can with this equation. Let's rewrite that down below here. Voltage is equal to 1 over C integral of I dt. If I is constant, let's say I is equal, I'll call it capital I, which just means it's a constant. If I is a constant, this equation simplifies, and I end up with V equals I over C times the time, T. Or I'd prefer to rewrite this as CV equals I T. So if I were to graph that, if I have a constant I for a certain time, T, I, so if I have a constant I for a certain amount of time, we'll call this value right here I, for a time T. The IT is the same as charge, Q. So the area under this IT curve right here is Q. So this equation then reduces to our familiar CV equals Q. Let me rewrite this as Q. Inductor versus a current, I, through the inductor. The equation is V equals the inductance times di dt. V dt. And I will explain what dV dt means in a moment. If I take the inductor, and I want to do a similar thing. I want to find an equation for the voltage across the bottom terminal tied to ground, and it has the value of capacitance called C. And over here I have an inductor with this terminal also tied to ground, and it has a value of inductance L. I want to introduce the current and voltage equations for a capacitor and for an inductor. Let's presume that I have a capacitor. If I want to write the equation for current in this capacitor I versus the voltage across the capacitor V, I come up with an equation. Current is equal to the capacitance C times dV